The equation we're going to use for this is the Boltzmann equation, which says that the number of atoms in the excited state is equal to the number of ground state atoms multiplied by the statistical values, which are equal to the number of degenerate levels, the number of ways we can put electrons into an energy level with the same energy, times the exponential of the negative energy of the excited state divided by Boltzmann constant times the temperature in Kelvin. We are actually looking for the fraction of atoms in the excited state, so what we'll do is divide through by n, and then we get the fraction of atoms in the excited state compared to the lower energy state. So again, we're going to look at to see what we know. We know K, that's a constant, that's the Boltzmann constant. Temperature we're given is 10,000 degrees. These statistical values, we're going to the 3p level. Okay, there are 3 orbitals that electrons can go into, 2 electrons in each, so that's actually equal to 6. And this is the 3s, so there are 2 degenerate levels there. So we know everything except we don't really know this energy, but what we do know is the energy emitted when an electron relaxes from the 3p to the 3s. So that must be the same as the energy required to excite it from the 3s to the 3p. So what we can do there, we need an equation to convert energy, which involves wavelength, and we know that already. It's the Planck's constant times the speed of light in a vacuum divided by the wavelength. The wavelength we're given is in angstroms, which is still a pretty common unit in spectroscopy. And 1 angstrom is equal to 1 times 10 to the minus 10 meters. So this is 5,893 times 10 to the minus 10 meters, or if we multiply by 1,000, 5.893 times 10 to the minus 7 meters. Okay, so we know wavelength. We know these constants, we can get energy. So Planck's constant is 6.63 times 10 to the minus 34. That's joules seconds. Speed of light is 3 times 10 to the minus 8. And that's meters per second. We have to squeeze that in. And divide by the wavelength, which is 5.893 times 10 to the minus 7 meters. Just draw a line to separate that. You'll notice that the seconds cancel out and meters cancel out, and we end up with a value in joules. So if we do that, we'll find that that energy is 3.375 times 10 to the minus 19 joules. And that's per photon. So we expect it to be a small number. Plug that into the equation, and we'll get statistical values. 6 divided by 2, so that's equal to 3. And the exponential of minus the energy, so times 10 to the minus 19 joules, divided by Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules Kelvin, times 10,000 Kelvin. So this should be per Kelvin. Kelvin cancel out, joules cancel out, so we end up with no units there. And what I would do is calculate what's in this parenthesis first, and that gives us 2.44. Take the exponential of that, multiply it by 3. So the exponential is 0.0866. That gives us 0.26. If you multiply that by 100, what that says is even at 10,000 degrees, which is the temperature in our ICP in a plasma, only 26% of the atoms are actually promoted to the excited state.